Give me 2 minutes. Okay, I'll join.
Yes, Naveen, let's start.
Okay, fine. Am I audible?
Yeah, you are audible.
Good. Uh, okay, guys, let's start the session today. And it's a demo session on industrial engineering. So I'll be dealing the section 4 for your batch. And okay, so let me go through the demo. And this is my background. So I did my bachelor's from Kharagpur and IIT Kharagpur and master's from IIT Hyderabad. Then I worked as a executive trainee in a PSU, that's in Ranchi. It's Heavy Engineering Corporation Limited, Ranchi. And after that, I left the job and to pursue PhD at IIC Bangalore. Right now, I'm in my final stages. So I have get teaching experience of 8 years in different subjects, teaching across India. And this is the syllabus for industrial engineering, right? So if you are in mechanical engineering, the syllabus of this industrial engineering will match with some of the syllabus in MBA program and some or BBA program. But basically, this is optimization. Whatever you see in industrial engineering, we deal with optimization. So this is some kind of a branch under optimization where we apply these optimization schemes to the manufacturing units or sectors. So that is what is the basic understanding of the industrial engineering syllabus in our mechanical engineering domain. So the syllabus comes as this. The first we'll discuss generally in our class we'll discuss inventory control, and then we'll start with operations research, and then we'll go back to this production planning control, and then we'll complete the syllabus like this, right? So today what we're going to do, we're going to introduce the basic topic of operations research. In that we're going to discuss this linear programming problem, and what is linear programming problem, who invented it, and who solved it first, and how we are going to solve it using simple graphical method. So we'll start with that. So if you have any doubts, please let me know. I'll be able to answer. Please do interrupt me in between and ask me the questions so that I'll be able to answer as we proceed. So actually, weightage is this, right? So if you see, this is like, I'm sorry for this, like this, the last 3 4 years, like I think I missed out. But anyways, like more or less, you'll be seeing the syllabus. The weightage will be around 4 to 5% in the sense like 4 to 5 marks, I can say. So it's having huge weightage, and manufacturing also is having huge weightage. So I can say the section 4 almost all will contribute 25% of the paper. I mean, maybe less than that. So 25 marks approximately, maybe 22, 23, 24, 25, like that. So approximately that amount of marks are asked from section 4. By that means you have to understand that what is the importance of this section 4, and it's very easy. It's not like tough, or like, say, tough in the sense like all are the same level. But what I mean is that these all topics are disconnected. There is no continuity from the previous topic. So it means that, let's say you're not good at some topic, let's say maybe forming, but you're good at welding, you can directly answer the forming, the answer from the welding. So what I mean is that it's not like fluid mechanics or maybe some engineering mechanics where you have to start from some, basic, and then you have to keep on building upon that. But the only problem here is that you have to have knowledge of all the things, in the sense like you have to have knowledge of mechanical engineering, you have to have the knowledge of electrical engineering, you have to have knowledge of mathematics, right? Like that. You have the two basics. It's not like high level, so you have to have some basics. That's it. So with this weightage, it's very important that you concentrate more on this, so that you'll be able to get good marks at the end of your, uh, uh, you know, gate results. Fine. So these are the books. So I would suggest these books for reference, not as textbooks, but as a reference books, because sometimes it's not all things possible that we discuss every aspect of the things. If you further want to understand more in depth the concepts, you can refer this. And also, I don't believe that it's not required for me for you to refer these books, because mostly whatever we discuss in the class that are sufficient enough. And we can go ahead with the slides that so after the session we will be able to provide the slides, so you can easily go through the slides, and that's enough. Practice the questions. Okay. And today, as I told, that we'll be discussing about linear programming problem, and that too will concentrate on graphical method. So let's start that. So what is operations research as in such? Okay. So the operations research is nothing but it's a tool which is used to make the decisions. So as I mentioned here, if you see, it is a scientific and mathematical approach to decision making that aims to optimize. As I was saying, it's all about optimization, right? What is optimization? Given certain scenario, you are trying to optimize some things. You are getting to the best out of all the things. That is what is optimization, right? So optimize the performance of complex systems from available resources. So let's say you're preparing for gate, right? And you're preparing for gate 2025, right? And exactly you have 1 year of time. So 1 year is some kind of a resource. Time is also a resource, right? So you have certain time, you have certain money, you have certain health, whatever it is. All these things are resources. Given all these resources, how best you can perform to get the best result, right? That is what is your optimizing. So you might optimize your time on a day, and you put a table, or maybe you're making a chart, time, day-to-day list, right? Changing the deadlines in the terms of completing the syllabus, and maybe writing the test series, that are all the decisions that you're taking to optimize your performance. The same way in the complex manufacturing system as well, we have this kind of available resources, and we have to use that and make sure that you get to the optimized performance, in the sense that the best performance available or reasonably available there, right? So it is also known as management science and operations management, which is very well read by these people who are doing this business and administration. And or is kind of shortcut for operations research, involves using mathematic models, the algorithms, data analysis. These days, the trend of AI. So basically, beside behind AI also we do optimize it, right? In AI also, if you go in deep, you do the machine learning, deep learning, whatever the things that are coming up these days. The background is all about optimization. So we are going to use this in engineering, business, economics, military operations, etc., etc., etc. But for here, we are using it in engineering, and that in the mechanical engineering and manufacturing sector, right? Especially we'll be dealing in that. Okay. So OR is to solve real world problems by identifying the best solutions based on the constraints, objectives, and available data. So this is what we are going to discuss today in detail. So what are the constraints, right? What are the constraints, and what is the objectives that you have to satisfy, and what is the data that is given, right? So based on these things, we'll be able to identify and understand and what. So what we have, what is the object? Let's say if you're preparing for gate, objective is to get good rank, right? What are the constraints? Time might be the constraint, resources might be the constraint, money might be the constraint. What is the available data? Data is what you have right now. Let's say you have certain amount of knowledge in certain topic and you don't have much knowledge in another topic. So that is a present situation. That is what is your data. Past experience, maybe you have written 2 or 3 times of gate, and maybe first time you got failed and second time you just reached the mark, and third time you wanted to go beyond and get a good rank. That is what is the present situation. That is what is the data, past data, right? So based on all these things, we'll be able to try to get make the objectives have the best possible solution. So what is objective? Get good rank, and best possible solution, getting under 100. So that is what is the thing that we are going to achieve. The same thing we are trying to project into the real world situations, right? So this overall topic covers wide range of topics, right, including linear, non-linear programming. But here in our GATE syllabus, we have only linear programming, and we have some network analysis, right, decision analysis. It's very important, right? So fine, let's not discuss much about it, and let's dive into the linear programming that I was talking about. So, linear programming initially was introduced by a person called George Bernard Dancing in the form of a beautiful algorithm called simplex method. Okay, that's a very beautiful algorithm, and that is the initial days of this operations research, and the initial days of what do you say, the optimization schemes, right? And then later on, if you go and see in the complex world, I mean, this is what is linear optimization. And after that, if you see, there is another person called Karmakar. I mean, this is the extra information that I'm saying you, because you have to have some motivation, right? So there's one more person called Karmakar who even did something called interior point method. So that's where the linear optimization has boomed up to non-linear optimization. And in non-linear optimization, there are so many people, right? There are so many people like Sobaisky, Newman, Heisenberg. There are so many people. And then that went to stochastic optimization, where there are some people like Taguchi and Sapner and all, right? There are some good people who did all this Gaussian process, neural network, genetic algorithms, transfer, and whatnot. They have so many things, right? And the present trend of the optimization and the future of the optimization is quantum genetic algorithms, quantum tunneling, simulated bifurcation. There's so many things, right? There is no end for it. But for all these things to run, let's say we have to understand the latest trend and do apply in your business, or maybe you have to apply in your job, whatever it is. The basic starts from the linear optimization, and that's where we are starting, right? That is the basic, and that is what you learn in your bachelor's. So let's start the linear programming problem, or maybe linear optimization. So here it's an optimization, tool in a 2D way. Linear programming we'll discuss in a two-dimensional variable, and then we can extend it to n-dimensional by using some other method. So linear programming is a mathematical optimization technique used in operations research field to find optimum solution with the constraints presented by the linear equations and inequalities. Please remember this. I'm talking about the linear equations and inequalities, right? So just keep these terms in your mind, and we'll be discussing ahead what is what as we proceed, right? So, in other words, linear programming is used for optimization of our limited resources. As I can repeatedly saying this, limited resources, limited resources. When I come to an example, then you'll understand what is this, right? Where when there are number of alternate possible solutions for the problem. So sometimes you have some alternate possible solutions. So what do you choose? Based on your domain knowledge, based on the current situation, you will be able to choose that, right? The goal of linear programming is to maximize the profit or minimize the loss. That is what is the meaning, right? Maximize or minimize a linear objective function. So basically, we have to set up the objective function, right? Without setting up the objective function, there is no point in optimizing something. What do you want to optimize? That is very important. What is your target? What is your goal? What is your aim? Right? Based on that only, you'll be able to do that. So if you want to achieve that target, goal, aim, or whatever it is, it is subjected to some constraints as well, and some on the variables of the problem. So you have certain variables. Based on the variables, you have constraints, and that constraints are used to optimize the objective function. So that is basically the linear programming. So now the next is let's go into some other thing. Let's start with an example. I make you understand how this linear programming problem objective function is developed, how the constraints are developed, and how do you solve it. So before that, let's see if a given problem is given. If a problem is given, sorry, I'm very sorry. If a problem is given in a descriptive way like this, so you can see the example here, consider manufacturing, making two products, whatever it is. The step one is to convert the descriptive part into mathematical model or a formulation. So once you form the mathematical model or formulation, then you use your tools to solve the problem. Right? First, this is the descriptive part. Then you have to convert that into your mathematical model. Right? So for an example, let's take this example. It's a very good example. So we'll stay with the example and we'll formulate it. We'll use the method that we'll apply the method that we know, and then we'll solve the problem, get to the results. Right? This will carry on till your end of your today's demo lecture. So let's go in detail. I'll explain very slowly and make you understand how to convert this descriptive part into mathematical equation. And then I will relate how this problem is, uh, modeled and then solved. And also maybe in between, I'll try to, there is another example. Maybe you can also try, pause the video and try. For now, I'll tell this. Then you can, for the next sample example, you can try it on your own, right? So consider a manufacturer making two products, A and B. So you can assume any product, maybe pen, pencil, some products that you come to your mind. But here I'm talking about a product A and a B. Okay. Two resources R1 and R2 are required to make this product. So here, instead of resources, maybe I can tell machines, right? Maybe two machines are required. That is also a resource, isn't it? Or maybe two materials are required to make a pen and a pencil. Right? Two materials are required. So in here, instead of because there is no commonality between the pen and pencil, what I'm talking about. So let's say if A and B are pen and pencils, R1 and R2 are machines. Let's say that, and both machines R1 and R2, both machines are able to produce these two products on each of the machine. In the sense, like A and B can be produced on R1 and as well as R2. That is what I mean. So let's take this. There are two products A and B, two machines R1 and R2, or resources R1 and R2 in a generic way. Each unit A requires 1 unit of R1. Right now, they are coming into the details. So let me make this thing into a 2D, box, kind of a matrix box, right? So let's make the row as A, two rows, A and B, two products, resources as R1 and R2, right? And they're saying each unit of A requires 1 unit of R1. Okay, it means that here 1 unit of R1 means, let's say A is product and R is machine. It may take 1 minute. That is what I mean. Maybe two resources are there. So 1 unit of resources, maybe you are making some material. So R1 is some material X and R2 is some material Y. Maybe for making the product A, you need 1 unit of material X. That is what is the meaning. Okay, and 3 of R2. So you need 3. So let's assume that if you are doing it, if you want to make A, you need 3 units of R2 so that A can be produced. Okay, and each unit of B requires 1 unit of R1 and 2 units of R2, right? So 1 unit of R1 again, 2 units of R2. So this is what is the thing. Now, so whatever I have filled inside are the units that are required correspondingly. Corresponding resources is required for the corresponding product. That is what is the meaning here. The manufacturer has 5 units of R1 and 12 units of R2 available. So total material availability for R1 or resource availability, I am writing here as 5. This is the total availability of R1. And total availability of R2 is 12. So this is the constraint that you're putting now. You're getting it, right? So now I'm going into initially I told okay this much is required, but now I'm telling this much is available. Whatever I've written this 5 and 12 is the availability. That is what is the constraint. That's very important. So we don't have any unlimited resources, right? At a given point of time. The manufacturer also makes profit of rupees 6 per unit of product A sold. In a sense, let's say if I'm selling the product, right? And what is the profit? The profit of A, if I just produce and sell one product of A, then I'll get the profit of rupees 6. And if I sell one product of B, I'll get rupees 5. You can see in the question. Right? This is the profit for A and this is the profit for B. Right? Now this is the profit. Now what you have to do, you have to allocate or you have to find out how many number of A's and how many number of B's that you have to produce so that given the resources, how many A's and how many B's you have to produce so that you maximize your total profit. Okay. So for a given resources, I can take, I can only manufacture A's. Maybe I'll take 4 A's. 4A if I manufacture, or what will happen? 4A if you manufacture, 4 into 1 this is required, and 4 into 3 this is required. So 4 into 1 is 4 into 4, 4 into 1 is 4, 4 into 3 is 12, right? 12 plus. So like that I can make. If you want to make 4A's, 4 into 6 is 24. 24 rupees is your profit. But that is not the maximization of the profit. It is some profit. Okay. So given these resources, maintaining these constraints, how many A's and B's are that you can produce is what you have to find. Right? So that is the basic setup of your uh, linear programming problem or linear optimization problem. Why I'm talking about linear optimization? Because here the variables are number of products that you're manufacturing, A and B. Number of A is X1, number of B products that you're manufacturing is X2. We'll go to that into the next place, but let's stop that here. So okay, let me assume that X1 is number of A's that I'm producing. X2 is this hash represents number of B's. And this is what you have to find. Okay, good. Now these two X1 and X2 are having some name, and that is what is decision variables. Well, let's go to the next slide and make it more clear. So this X1 and X2 are decision variables because you are deciding this based on the given profit, given constraints, right? Decision variables. X1 is the quantity of A or number of A's produced. X2 is number of or quantity of B's that will be produced. That is the important thing. Okay. Now let's say if you're producing X1 A's and X2 B's, so what will be the resources that is required, right? So total resource requirement, right? The total resource requirement for R1 is how much? So you're making x1 is x2 b's. So I can write x1 into 1 plus x2 into 1 is your total resources that is required, isn't it? So for R1, it is x1 into 1 plus x2 products you're making for B, x2 into 1 is your the number of resources required for making B. Now this is your total. This is your total total resources requirement. But what is the cap? The cap is 5. For a given situation, in this situation, you cannot exceed to use this number of R's, R1s more than 5. So what I would do is I'll put a constraint that I would write in a different ink here. So I'll say this x1 plus x2 should be less than or equal to E5. And this is what is your limitation for resource 1. R. And that is what is your constraint. In the same way, similarly, you can go and find out for R2. For R2, what is that? X1 into 3 plus x2 into 2, isn't it? So x1 into 3 plus x2 into 2. And what is the constraint? What is the cap that we have? The cap is 12, right? So we will write x1 or 3x1 plus 2x2 should be less than or equal to how much? 12. And I repeat again, this is the limitation for resource R2. Okay, it's very important. So now you see, we have already, without knowing, we have completed the constraint. So if you go back, constraints, constraints, constraints. So these are the constraints. X1 you're making A, X1 A's you're making, X2 B's you're making. So X1 plus X2 should be less than or equal to 5. 3x1 plus 2x2 should be less than or equal to 12. Right? These are the constraints. Now, what is the objective? The objective is to maximize the profit. Okay? So, if you are producing x1 A's, 6x1 will be your profit on A. 5 into x2 will be your profit on B. The total profit will be 6x1 plus 5x2. And that is what is your objective function. That is what is your objective function. Right? So, if you see, can see here in our case, especially in our case, there we are talking about the profit. So we want to maximize the profit, right? So if you have some profit kind of a situation, you have to maximize it. That is what is your aim, right? So you have a profit. Yeah, you will go for a maximization, right? And on the other hand, if you have a loss equation, or you want to try to have an equation or objective function which is loss, then you have to try to minimize it, right? So minimize it, sorry. Okay, are we having any doubts till now here? Anyone who's here who's having any doubts? Okay, okay, fine, no issue. Okay, I think let's proceed. Now, if you try to understand the profit equation in our case. That is, so the objective function generally, so we in our case this is this, right? So I'll write Z as, what is the total profit for each one? 6 into x1, 5 into x2, because if you're manufacturing x1 A's, so let's say 3 A's you're making, so 3 into 6 rupees your profit, right? 2 into 5 is your profit for B, like that, right? So 6x1 plus 5x2. And what is the name for this? The name for this is your objective function, right? Now we got to know the objective function, we got to know the constraints. Let's write this in a single way and understand. So what then what we are doing? We are trying to convert the descriptive part into the mathematical formation. Ultimately, we did it. So the formulation, the total formulation. So the formulation is Z. You want to maximize it. Let's say Z max is equal to 6x1 plus 5x2. Sorry, here I wrote x1. It is x2, right? And you remember here, this is objective function and this is linear. Why? Because you don't have any degree for this variables x1 and x2. So that's why it's linear optimization, right? These are subjected to, this is subjected to, this is how your questions will be asked if they are giving directly the mathematical formulation. That is, what are the subjected to? X1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, right? So x1 plus x2 will be less than or equal to 5, 3x1 plus 2x2 should be less than or equal to 12. Okay, and these are your constraints. Okay, now please remember there is one more constraint called non-negativity constraint, and that is obviously you cannot produce negative number of products. It will be zero or more than zero, right? So I'll write x1 is greater than or equal to zero, x2 also will be equal to greater than or equal to zero. This is implicitly assumed, but if you want to write explicitly, this is called non-negativity constraint. Because I'll tell you why this is useful. Because when you're plotting the graph, so this will be useful for us. Okay. So now, what are the important things that are there in linear programming problem? Let's list them down. Right. So requirements. Right. What are the requirements? First, we have to have a objective function. Right. Maybe we have maximization of profit, or we can write as minimization of loss. Okay. And what is the second thing that is required is your constraints, right? So constraints is restriction on resources, available resources. And the other things is simple non-negativity constraints. Good. So that is what I have clearly mentioned here. Objective function, it is the function which we need to optimize, and it should be clearly identifiable and measurable in a quantitative terms like maximization of profit, sales, and minimization, whatever it is. So if want to write in a generic way, then we can write it as z max or maximization of z can be written as some c1 into x1 plus c2 into x2, right? And so on, so on, so on, so on, some cn into xn. So the cj's are nothing but profit coefficients that are profit values, right? And xj's, I can call them as decision variables. That's what I already told you, decision or choice variables, I can also say. Good, right? In the same way, already I have put it because I don't want to write down. So constraints can be written as less a11 x1 plus a12 x2 plus so on till a1. This is a generic representation of a requirement of linear programming problem. Okay. So this a1 and all these things are technological coefficients for substitutions in the sense like what are the available values, what are the resource values that are available, and x1, x2, x3, so on are choice variables, isn't it? And this b1, b2, b3 are your resource variables or the cap on your resources, restriction on your resources, constraints. These things are called constraints. In the same way, we have non-negative, that is all the variables, decision variables should be greater than or equal to zero. So that's why they are called non-negative or non-negativity constants. Good. So all the variables in the object function and constant should be linear and non-negative. So those are all linear. So now let's go. Okay. Now that you understood what is the requirement, so this is another problem, but I'm giving an example. So that problem will stop for there, and we'll continue after this small example in between. So I will give you some time. Okay, maybe if you're watching this as a recording, what you can do, you can pause the video and try to, you know, uh, solve the problem and proceed for the solution. Okay, so let me proceed with the solution. So a manufacturer produces two types of models, M1 and M2, maybe some car model or some kind of a model. Okay. Each model of type M1 requires 4 hours of grinding and 2 hours of polishing. So it means that model M1 and M2 both are requiring this operations called grinding and polishing. And whereas each model of M2 requires 2 hours of grinding and 5 hours of polishing. Both are required. So let me make a grid again. Okay, 2 cross 2 grid. Because here, why we are making 2 cross 2? So if you are trying to solve a problem using graphical methods, you are going to plot it on a two-dimensional plot. So if you're trying to plot it on a two-dimensional way, so you need to have only two decision variables because x1 and x2. X1 is x-axis, x2 is y-axis. If you want to go for a three dimension, you have to increase your dimension. It's difficult to draw it on a 2D paper, right? You have to go to some three-dimensional computer thing. Four-dimensional, five-dimensional, it's impossible for us to make a plot, right? So if you have that kind of decision variables, there is another method called simplex, and that's what we're going to discuss in our daily classes, right? So let's continue with this. So I'll make a grid of 2 comma 2 like this. Okay, what they're saying, machines. So let's say the machine or models, model 1 and model 2. So I can say these are models, these are models.
You are currently the only person in this conference.
Yeah, Naveen, you can start.
There's some problem with this share screening.
Yeah, now you can.
Okay, so sorry for the interruption. There's some technical issue here. So now we have this models M1 and M2, and now we have these two, maybe I can say processes. Okay, grinding and polishing. So these are your processes, right? Now they're saying what? 4 hours of grinding and 2 hours of polishing. 4 hours of grinding and 2 hours of polishing. For model M2, 2 hours of grinding and 5 hours of polishing. The manufacturer has two grinders and three polishers, right? So now what he's saying, he's having limitation on grinders. How many grinding is he is having? Two grinders and two polishers. That is the limitation. But this is hours, right? So we'll convert that into hours. Okay. So each grinder works for 40 hours a week and each polisher works for 60 hours a week. So if we have two grinders, each working for 40 hours, the total grinding hours that are available for us are 40 into 2, isn't it? The 40 into 2 is 80 hours here, okay, for grinding. And for polishing, it is three polishers and each polisher will work for 60 hours a week. So it is 3 into 60, that is 180 hours a week. That is the cap limit, resource limit. And now, whatever is produced in a week is sold in the market. How should the manufacturer should allocate his production capacity of two models so that so the profit on model M1 is 3 and profit on M2 is 4. So we can directly write the profit here. So this is your objective function, right? That is your 3 rupees on model M1 if you're producing it, 4 rupees on. So again, you can take x1 number of A's or x1 number of M and x2 number of M2 that you're going to manufacture, and these two are your choice variables or decision variables. So this is how we have to select first, right? Decision variables. Now, after that, what are you going to do? You're going to write the constraints. Constraints you can write easily. That is 4 into x1 plus 2 into x2. The total number of grinding hours is less than or equal to 8. Right? So we can write total grinding time constraints. What I'm writing are constraints is 4 into x1 plus what is that? 2 into x2 should be less than or equal to 80. These are total grinding hours required if you're making x1 M1 models and x2 M2 models. So it should be less than or equal to 80 hours. That is the cap because you have two grinders working 40 hours a week, right? 2 into 4, 2 into 40, 80. And total polishing time is 2x1 plus 5x2 should be less than or equal to 180. right? Now we got the constraints. We got the constraints. So what are the other two constraints? Non-negative constraints. That is x1 should be less than greater than or equal to 0. X2 also should be greater than or equal to 0. These are non-negative constraints. And what is your objective function? You have to maximize the profit. Right? So maximize the profit. How much profit you are getting if you're selling M1? 3 rupees. If you're selling M2? 4 rupees. Right? So total profit is 3x1 plus 4x2. Right? This is your objective function. That's it. So this is how you convert the mathematical description into a formulation such that we can use some other methods to solve the problem. Right? So now let's go into the next one where we're continuing with the previous one. So that was this. This is 6x1, 5x2, and these two constraints. So same thing I'm going. So we have completed with the step one, that is converting the description into the mathematical formulation. So once we are done with that, once we have this formulation like this, then we are going to use this graphical method to solve it. How are we going to solve it? The step two in the graphical method is, that's why I wrote the graphical method here, is first you have these things given, right? If it's not given, you have to convert that you know. And the next step is plot the linear constraints as equalities on x1 and x2 coordinate plane. And then plot the non-negative restriction, restrict yourself to the quadrant 1 only. So they are saying you to plot these constraints, constraint 1 and 2. Considering the non-negative constraint, it means that if you have a plot like this, x1 and x2, they're telling us to plot these two lines as a linear values. And they're saying that you be only in quadrant 1. Don't go to quadrant 2 and don't go to quadrant 3 and 4, because this will be violated if you're plotting something in quadrant 2, 3, and 4. Only one is, that you have to maintain. So to do that, so they're saying given linear constraints as equalities. This is important. As equalities, you have to do. So here these are inequalities. Whatever you are seeing here, inequalities. You have to consider that, convert that into equalities. How you do? You have to make it equal to 0. That's it. Okay. So let's do that. So how you going to do that? So if you're taking this first constraint, x1 plus x2 will be equal to 5. And what you have to do, when I'm just trying to plot x1 is equal to 0, what will happen? X2 will be 5. That is what is, if you're putting x1 0, x2 is equal to 5, isn't it? So the point of x comma y, x1 comma x1, x2, because I want to find the points, right? So it will be 0 comma 5, isn't it? And when x2 is equal to 0, then that's the result, x1 is equal to, so this will be 5 comma 0, isn't it? In the similar way, if you take this constraint, 3x1 plus 2x2 should be equal to 12, right? I'm converting into equality sign, right? So when x1 is 0, what will happen? X1 0, 2x2 is equal to 12, x2 will be 6, 12 by 2, right? X2 will be 6. What is the coordinate you are having? 0 comma 6 for this constraint. And when x2 is equal to 0, then you have the coordinate 2 is equal to 0, 3x1 is equal to 12, x1 is equal to 12 by 3, that is 4, so x1 is equal to 4. So what we have, the value as 4 comma 0. Now with this two, I will go to the plane. In the sense, I'll plot two lines, x1 and x2. Those are the axes, and then I'm going to plot all these four values: 0 comma 5, 5 comma 0, 0 comma 6, and 4 comma 0. So this two will give you one line, and these two will give you one line. So it means that you're trying to plot this line and this line. Right? Let's plot that. So plotting the feasible region in first quadrant. So that is what we are going to do, right? So there is another difference between feasible region and infeasible region. You forget about it. I'll tell you what is that. But before that, we are doing the step by step thing. Let's do that. So if you take something like this, just making it big, so that will be good for you to understand what I'm doing. So maybe I'll do like this. So I'll split this 1, 2, 3, 4, 5, 6, something like this, right? So, and this is your x1 and this is your x2. In the same way, I'll plot here 1, 2, 3, 4, 5, 6, 7, 8. Why I made 7, I'll let you know. Right. So this is 1, 2, 3, 4, 5, 6, and so on. And this is 1, 2, 3, 4, 5, 6, 7, and 8, and so on. Now we are going to plot these two, 0, comma 5 and 5, comma 0. So where is 0, comma 5? So let me take some other thing. So 0, comma 5 is this. Sorry, 0, comma 5. Where is it? Okay, 5, comma 0 is this, right? So this point is 5, comma 0. 0, comma 5 is this. Now draw a straight line between that, right? So if you want to draw a straight line between that, right? You got a line like this. Okay. So this is your straight line. Okay. So okay, I can't erase like that. Let me do one thing. I'll draw it white. So you have to not cross that. Please remember, you should not cross that. Okay, you should not cross that. Please remember that. Okay. And this is your what? 0, comma 5. And what is the other one? The other one is 3x1 plus 2x2. So here 6, 0, comma 6 and 4, comma 0. So 4, comma 0. Let me take another ring. 4, comma 0. And another is 0, comma 6. 0, comma 6. Draw a straight line. Draw a straight line connecting these two. Right. So this is 0, comma 6 and this is 4, comma 0. Simply remember, I'm not crossing the quadrant itself. I'm being in first quadrant. It's very important. Okay. Now once I draw this, let's say here, before drawing this green, only we are talking about purple. Okay. So let's say you want to, you have plotted the linear, but what the constraint says, it's an inequality constraint. It is less than or equal to 5, but you have plotted whatever this line is equal to 5. But if you want to find out what is less than or equal to 5, what you have to do is that if you are having an issue, try to substitute. So what is this? This is your origin, isn't it? This is your origin, right? So if you substitute this origin into this constraint for the given constraint, if it is satisfying, so if you're substituting 0, comma 0 here, it is 0 plus 0. Obviously, 0 is less than 5. So this origin is satisfying this equation. It means that you have to shade. You have to shade like this towards the origin. Like this. With some patterns. Okay. And again, the shading also, we are not going into other quadrants, 2, 3, 4. Only we are shading it in first quadrant. It's very important. Now this shaded area region will represent this complete constraint. Okay, you take any value in this shaded region, including the line of the axis as well as the purple line, the line x1 plus x is equal to 5. Substitute here, you'll be satisfied, and that is what is feasible. That is what is the feasible region for that constraint. And in the same way, you substitute 0, comma 0, that means origin here because origin is here. So you substitute again, this also will be satisfied. Again, you have to right shade in origin direction. That other one as well. right? Now you take any region, any point in this green color region and try to substitute into this inequality, it will satisfy. Now, but we have both constraints. So these both constraints have to be maintained for this solving this problem. So what I'll take, I will take the common region. I will take the common region for both of it. What is the common region for both of it? Common region, the common shaded region is this. There's a point there, intersection point of the both lines. So if you want to find out the intersection point, this you just take x1 plus x2 is equal to 5 and 3x1 plus 2x2 is equal to 5. You find the common point, you'll get the point as 2 comma 3. Just it's a simple mathematics. Just intersection point you can find out. Okay. Now what I'll do, I will next step is find out. I'm going to do it here itself, but find out the corner point of feasible region and find the values of objective function at the corner point. So now I'm just going to plot this in the next line, next plot. So simple plot, same thing I'm projecting. How it is looking simply on an average I'm saying. So this is your x1, x2, sorry, right? So what I'm doing, so this is your 0 comma 5. I'm plotting only common region 2 comma 3 and 4 comma 0, right? Something like this 2 comma 3 and 4 comma 0. This is 2 comma 3 and this is 4 comma 0, right? And this is your 0 comma 0. So that is what is mistaking it, common region, right? So this is your common shaded region, right? Now what I'm going to do, I'm going to find out the corner points. What are the corner points? Corner point 1, A, B, C, and D. So find out the corner point of feasible region. So this is the feasible region. Okay, this is the feasible region for the given problem. Because you take any point in this feasible region, substitute in both the constant equations, it will be satisfied. So that is why it is called feasible region for this problem, for this given constraints. And also it is all the points will be selected from the first quadrant. Obviously, both x1 and x2 will be greater than or equal to 0. That also is maintained. So all the constants are maintained. Now what are you going to do? You will find the values of objective function. What is the objective function here? The objective function is 6x1 plus 5x2. Right. So let me write the objective function here. The objective function is z is equal to 6x1 plus 5x2. You have to find out you have to evaluate this objective function at each corner point. So let me jot down all the values. So a 0 comma 0, b 4 comma 0, c 2 comma 3, d 0 comma 5. For each, sorry, let's make a barrier here. So at each point, what you're going to do, you have to evaluate this z. If you are evaluating this z, this will be equal to 0 plus 0, 0. 6 into 4, 24 plus 0 is z is equal to 24. And 6 2 is 12 plus 5 3 is 15. 12 plus 15 is 27. And 0 into 6 is 6. 0 plus 5 into 5, 25. So this is 25. Just evaluating this values and this. That's it. Substituting that and try to find. Sorry. Okay. Now, what are you going to do? You have to find out the maximum value out of all these objective values. Where you're getting 0, 24, 27. So 27 is the maximum value. Maximum profit. So hence point 2 comma 3. It means that x1 is equal to 2, x2 is equal to 3 is the solution for your problem. In a sense, you have to make x1 A's and x2 B's to manufacture to get the maximum profit. Okay, so that is what is very important. Okay? So that's how you have to solve the problem using your graphical methods, and that is how you have to find out the try to convert the descriptive part into the mathematical formation, and then trying to find out the objective function constraints, try to plot that into a 2D graph, and get on to the finding out the feasible region by shading it, and then finding out the corner points and evaluating the corner points for the objective function, and find the maximum value of your objective function, and then at which point of the objective function is maximized, and that is what is your solution. So that is what is the graphical mathematics. So there are so many other things, like there are some different cases that we are not going to discuss now, but we are going to discuss in our complete classes. So the case one is here the solution. What if there is no solution? What if there is no common feasible region? What if there is no unboundedness? There is it's keeping on going. What if there are some multiple solutions? There are different cases that we're going to discuss. Stay tuned. If you're going to join us, we'll be clearly discuss all these things. We'll have very nice sessions together and enjoy it together. Okay. So thank you for listening. And if you're watching the video later on, thank you for watching the video. If you have any comments, please do comment and let us know. We'll be able to answer your queries. Thanks a lot, guys.
Yeah, yes, Naveen, anything? We can continue.
Yeah, Dinesh, please.
Yeah, yeah, done, right?
Yeah, I'm done. I'm done. So this is where we stop because there's another thing that I don't want to take. It will take some time. Yeah.
Okay, fine. Fine
So
then.
I mean, anybody can
Yeah,
comment
yeah,
it and
sure.
you know
Yeah.
discuss upon that.
Okay, okay then. Thank you, Naveen, and thank you
Yeah,
all for watching this session. We'll wind up. Thank you.
sure. Thank you.